Hey there, Stephen Barter here. How are you doing on this great day? Me? Well, I'm somewhat excited to be honest, because I'm about to share with you one of the most valuable lessons that you can learn in extrusion blow molding. And you know what? It's not that complicated. But I'm also somewhat confused, because I don't understand how this information has escaped so many molding shops. Well, until today. So I'm excited, I'm confused, and I'm going to tell you more, all on Pro Molder Lesson 1.
So today we're going to talk about the mould is a heat exchanger, and specifically water cooling. Now thinking about your mould in this context really does open your mind to all the keys to getting the best from your mould and the moulding process. So why is it so important? Well, if the heat exchanging process is not working correctly, it will give you significant variations in quality, increase the cycle time, and damage the mould through thermal expansion. This heat exchanging process for today's lesson is one of the most important lessons you will learn, and is why this lesson is at the very beginning of the program. And we'll cover two of the four most important control factors in moulding a bottle. So heat exchangers do exactly what their name suggests. They exchange heat in the process. In our case, the mould removes heat from the plastic and transfers it into the water travelling through the mould. This needs to happen efficiently, otherwise our cycle time will suffer and the quality of the bottle will be variable. Hot spots in the mould will create thermal expansion and wear out mould parts prematurely. So how does it work and how does it happen efficiently? In the moulding process we use high pressure air, let's say at around 100 psi, to hold the molten plastic paraffin, let's say at 180 degrees Celsius, against the mould cavity. Now the plastic must be firmly pressed against the wall of the cavity by the air pressure for the transfer of heat from the plastic to the mould, steel or aluminium, whatever the construction might be, and then into the water being supplied at around 60 psi pressure and at a temperature of 12 degrees Celsius. Now only if all these steps occur within the right ingredients as I described, then we'll have efficient heat exchanging. If just one of these steps is compromised, then the heat exchanging process will break down and the quality of the bottle will suffer. The typical response to this sort of behaviour is to slow down the cycle time. Importantly, in Lesson 2, we will cover off the air pressure and paraffin melt temperature in preceding lessons. In this particular lesson, we're only going to look at the cooling water itself. So the most important phrase I have lived by for many years is pressure is result of resistance to flow. And I'll say that again. Pressure is the result of resistance to flow. So this is basic hydraulics. So why is this so important? Well, water is basically lazy. It'll take the easiest way in any situation, and moulding is no different. So if we do not supply enough water, that is the volume to the mould, then the pressure will not build up as a result of the resistance to flow. The water will just freely find its way through the mould, therefore we must supply more water than the mould can actually use. And I'll say that again, we always need to supply more water to the mould than it can actually use to create that pressure. So what happens if the water volume is too low and the pressure is not there? Well, we get what's called preferential flow. The water will travel through the mould in any way that it has the least amount of effort, and this is much worse when we have multiple cavity moulds. So again, multiple cavity moulds use a lot more water than single cavities. The water cooling channels will be filled with a combination of water and air pockets, which will move around the mould. The air pockets do not remove heat from the mould, and as a result the mould will heat up in locations with air pockets exist, and the water flowing without resistance does a very poor job of removing heat from the mould. A typical response to an unknown flow situation is to reduce the water temperature to try and make the mould cold. This may give an impression of an improvement in the situation, however in reality what is happening is a combination of hot and cold spots in the mould is introducing stresses into the bottle. And this will cause instability in shrinkage. Sizing will also be incorrect. Now I would typically run my chill water supply between 12 degrees Celsius and 16 degrees Celsius depending on the environment. In most cases I will choose 16 as I can run this temperature all year round and not have too many issues with condensation in the summer seasons. And it also means that my recipe doesn't change, and that's probably the most important thing, is having that consistency all year round. So just while I'm discussing condensation, when this occurs, a typical corrective action is to partially close the water supply down to the mold. Now this is really bad as it changes the flow characteristics of the water and creates that preferential flow I was just talking about. So if you find yourself in this situation and you cannot run higher water temperatures, I suggest that you close down the outlet only. Now this will reduce the air pockets by keeping the channels pressurized. So the most important step you must take now is to measure the water pressure coming into the mold and the water pressure coming out of the mold. So how you do this is equally important. Now creating restrictions in the water circuits with fittings etc. where you want to plug a gauge into and if the internal size is incorrect will give you a false reading. This is basic hydraulics, so I suggest you read up on Bernoulli's principle on pressure and flow, and that's where I got the foundations for my learnings from. So measuring the pressure coming into the mold will tell you if there is enough water volume coming to the mold. Remember, if there is not enough volume coming in, there will be very little pressure. So pressure is our guide here when we're looking at measuring the mold performance. So again, measuring the water pressure coming out of the mold after measuring the water coming in will tell you what's going on inside the mold and the pressure drop across the mold. So this will determine if the volume is correct. Now a pressure drop is absolutely critical. If the pressure coming in and out of the mold is the same, then there is no flow. You actually need a pressure differential to create that flow and to get the water to actually move through the mold and carry away the heat. Again, that's coming back to that whole heat exchanging process. So an example would be, if you have good inlet pressure, and let's say 60 psi, it's the same on the outlet, and chances are there is a blockage further along the line. On the flip side, if you have pressure is high on the inlet and very low on the outlet, indicates that there is a restriction in the mold itself. Now this could be anything from poor design right through to a breakdown in the water circuit, or maybe even a combination of both. So when I'm doing these tests, what I'm looking for is a number around 20 to 30 psi differential. I'll say that again, 20 to 30 psi differential. Now this indicates to me, from a lot of experience and a lot of experimenting, that the mold is being fed water correctly. And I have a preference for the supply at the mold to be 60 psi in almost every scenario. And again, this is all from my experience and experimenting. And if you see a pressure drop of only 20 or 30 psi on the supply, you will get preferential flow. So just as a secondary quick test, sometimes I would actually measure the water temperature coming in and out of the mold. Now there should be no more than 1 or 2 degrees difference. If there is, then there is a problem with the flow, and you're going to need to investigate that one as well. So if I don't get the pressure differential that I'm looking for, I do a number of things, of course, depending on the results of my checks. I'm going to use this Excel file here, if you like to follow these, just to show you what we're going to be working on. So low pressure supply at the mold. Well, this typically means the mold can use more water than is being provided. So the mold is actually being starved. So in this case, I check the supply coming into the machine. I found to achieve 60 psi at the mold, I would need about 100 psi at the supply inlet to the machine. This will of course vary depending on machine size etc. However, it's a good rule of thumb and I've found it to work very well for me every single time. If the supply at the back of your machine is low, say it's less than 60 psi, then I would go back and have a look at the pump system and see how it can be boosted, or if the pipe structure is too small and has restrictions as well. If the supply pressure is close to 100 psi, I then check the machine and the mold pipes, hoses, etc. and look for any sizing or any restrictions with small pipes or fittings that may be restricting the flow somewhere. If the pipes and fittings are okay, then I'll open up a cooling system, look for blockages working backwards from the mold. This is a very common problem. I have seen many manifolds, for example, completely blocked and water fittings rusted and blocking the water flow entirely. Finally, the last reason you may have an issue is the mold cooling is being shared with other features of the machine like cooling of the hydraulics. If this is the case, then the only resolution for this particular issue is to increase the size of the pipe supplying your machine. Now let's look at a low pressure differential on our mold. Now assuming you have the correct pressure at the mold, this simply means there is a blockage after the mold. In other words, the water just simply cannot get out of the machine. So what I'd do is I'd follow the same process as described earlier and look for problems in the return lines working from the mould and moving towards the return tank in your cooling system. Quite often it's a simple problem of blocked lines, rust, some sort of build-up. So with the high pressure differentials, and this is a very different story. So if we have a high pressure differential at the mould, this is where the mould has a restriction internally, assuming you have checked the fittings are correct and the sizes and functioning correctly. So the mould needs to be pulled apart and the water circuits cleaned and any rust or foreign materials moved. Now rust is not a good conductor of heat and will also inhibit the good heat transfer. So just remember that any coating on the inside of your water circuit will actually reduce the cooling efficiency of the water. So lastly, I've seen a number of mould designs with water circuits that actually inhibit the flow of water. So to use an example, a 90-degree bends actually slow down the flow of water, and as a result there is a loss of volume and pressure after the 90-degree bend. And moulds are basically constructed with water circuits that bend in 90 degrees and even 180 degrees. So at each one of those bends there is a pressure drop. So when you're designing your mould, one thing you do not want to do is have lots of bends at the very beginning of the supply circuit of the mould. And mould designs, water circuits, we'll actually cover in a later lesson as well. Okay, so once you've done all your tests and you've gone through your machine and you've found the problem, what you need to do is make sure that when you're working with your team, you need to prevent the same problem occurring again, particularly with rust and other water problems. So in a later program, we're going to discuss this problem-solving process and corrective actions, how to define your problem properly and how to come up with the correct corrective action. So let's just quickly review the main points that we've discussed here. Pressure is the result of resistance to flow. That is such an important lesson, and think about that in every component of your moulding process. You need to know what your cooling system and moulds are doing with the water supply. Any issues must be fixed. If you don't fix them, then you're always going to have problems. Water temperature should not be lowered to compensate for poor supply. I recommend running between 12 and 16 degrees. What this means is, regardless of the weather conditions, I can run the same water flow and the same water temperature all year round. So your homework for today is to go out there and check your mould water circuits. Remember, when you're using a gauge to measure your pressure, don't restrict the water flow in any way, otherwise you will get a false reading. So I'm really keen to hear about your results. So if you like, put them on our blog page. It'd be great to get some feedback, and maybe we can even discuss your results as well in a later call. But most importantly, never ever assume that it is okay. If you suspect it okay, or you have an opinion that it's okay, that is not good enough. You need data to support what's going on. Okay, so looking forward to hearing from you. Make sure you go and check your mould water pressure. Well, I hope you found this information valuable, engaging, and fun. But most of all, make sure you use it. It's not worth anything to you until you use it and actually take some real good solid action. Make sure you tell your colleagues to subscribe and keep our program growing. So that's it for today, folks. Until next time, have fun moulding a bottle.